silver, something like point something percent. When there is no silver but only bismuth, there is a small effect. And there is first a damping, increase of the line, of the FMR line, that says that there is some absorption of the spin currents, and there is a small voltage here, V. But this signal becomes very large when there is at the same time bismuth and silver. If there is bismuth at the bottom, silver, and then the permalloy, and this signal becomes very large and can be ascribed to the inverse Edelstein effect. This one is more, sometimes it can be due also to some smaller inverse Edelstein effect at the interface between permalloy and bismuth. But as I said this morning, I've commented this morning, certainly the competition between exchange and spin momentum locking makes that the effect is larger, smaller when there is no silver. One of the recent results that we have by one of my co-workers is that he changes the order of staking. That is now bismuth above silver. And so this effect is reversed. This is in agreement with what is expected by the symmetry, because what is important is the direction of the electric field of the interface. So by changing the order, then we have the opposite effect. Or if you want, by adding here silver below bismuth, makes that this small effect become an effect of opposite sign in the opposite direction. That is compensated by a larger effect related to the bismuth-silver interface. So this is for the current derived by the potential, so the current divided by the resistance of the system. And again, so I always say that IC is reversed by adding bismuth below. This is the result for several samples as a function of the thickness of silver. So the effect does not depend very much in many series of samples for the thickness of silver. Of course, it's negligible when there is only silver. It's small when there is only bismuth. But as a function, when there is at the same time bismuth and silver, the effect is more or less the same. And it can be there. Okay. So this is the current density. In this plot, I have plotted the current density. That is current divided for a two-dimensional system divided by the width of the stripe. So, in fact, the effect can be characterized by the ratio between the three-dimensional spin current, between the two-dimensional charge currents in amps per meter. It's a two-dimensional current density. The ratio to the spin current that is injected, that is a three-dimensional, that is ampere per meter square. And so the result that we obtain is this ratio that is a length, of course, because it's a ratio between two-dimensional to a three-dimensional currents. So the result for several samples, and in the paper that we have published are even more samples, we obtain that the system is characterized by a given value of lambda. So what characterizes the conversion between spin to charge currents is this a sort of constant value of this length, lambda, length of this Edelstein effect. And interpretation, of course, is what I have already mentioned a few slides before, is that when we inject, we have shifting. We are introducing this spin direction, shifting this contour on this side, shifting the other contour on the other side, and the calculation of this effect gives this value for lambda. That is the Rashba coefficient divided by h bar and multiplied by tau, which is the time of relaxation of this out equilibrium distribution. This is the out of equilibrium distribution with a given current and a given spin density. Is neither a momentum relaxation. Neither is because there has spin momentum blocking. This is only the relaxation of this out of equilibrium distribution. And actually, we found something which is around 0.2, 0.3 nanometer for this lens, typical of this interface. And in fact, similar recently, but this paper has been now published in PRL, is by the Vignal, Certainly, and Raimondi. They treated the same problem but in a different approach. This is an approach based on this picture, on this ground state, the picture of large Rashba effect. That is, the ground state is the Rashba state. They are simply introduce the Rashba coupling as a perturbation. And then, when they introduce the Rashba coupling as a perturbation, they have a spin relaxation time and a momentum spin relaxation time. But they find the same expression, but tau now is the momentum relaxation time. But this is exactly the same expression. What I can say also that the problem with the surface states of topological insulator is the same. In fact, the same expression can be worked out, except that now the ratio alpha r over h bar is replaced by the Fermi velocity of the cones. So you can extend this sort of model to this type of situation. So the practical question is how to distinguish this interfacial contribution, Rashba effect, or topological insulator effects, from the bulk effect, the spinor effect. In fact, if one compare the situation where one inject a spin current into, say, platinum, and the situation when inject into the Rashba interface, in fact, the equivalent of the two-dimensional current, total current divided by the width, is obtained by integrating the three-dimensional current density of the spinor of the classical expression. That one obtains this expression for these two-dimensional spin currents to be compared to this one. And suppose, for example, for simplicity, that we are for a thickness much smaller than the spin diffusion length, then one obtains that this ratio, two-dimensional charge current density over three-dimensional spin current density is given by the thickness multiplied by the speed or angle. And in this situation, 2 lambda to this characteristic length that we have extracted for the Bismuth-Silver interface. So, in fact, if you want to interpret, you say, okay, I have silver here, I say I want to interpret these results with a constant lambda by some spin or angle for silver, say for silver, for anything. So I have to identify lambda to this product. And so that means that then this will lead to fit with a constant lambda to a spin or angle will be inversely proportional to the signal. So if we want, for example, interpret our result with a constant lambda to something due to silver, this will give for silver this or angle as a function of the signal. So that means simply that it's not physical to interpret this effect by a spinor effect, which is a spinor angle with is a three-dimensional concept. Also, if you want to say it is due to some metal conducting layer of 2 or 3 atomic layer, this will give a spinor angle of the order of 200% or 300%, something very high. But these have no physical meaning. For example, and the difficulty is, of course, to separate the spinor effect and this possible interfacial effect. For example, if I look this result at Cornell for tungsten as a function of the thickness of tungsten, one sees this upturn. Certainly, this is a good reason for the upturn is the increase of the radiation of tungsten and the crossover to the. But maybe there is also a contribution for some interfacial effect. fact, the interface effect would give rise, in the interpretation by spinor effect, to something in one of the T. So certainly one difficult problem is to separate these two types of contributions. Okay, so now I will proceed to the application to the mainly to the motion of domain walls. In fact, if we have a spinor effect, you know already these two types of quark, different symmetry that induced by the spinor effect in a platinum layer. It can be the same expression also obtained if one take into account the polarization in this bottom hash bar interface, because then it gives rise to also to a by diffusion to a spin going upward. And if we have the hash bar interface just at the interface with the ferromagnetic film, then we have mainly what is expected mainly generally is field-like term, which should be important, but certainly according to the theoretician, is also there is and according to what we have seen this morning, there will be also an anti-damping term, maybe smaller. And so I begin by saying we have investigated what can be done with all these effects with different type of domain walls, in plane, block, near, with different direction of the current in the spin orbit layer, longitudinal or lateral, and by introducing these two types of terms. In fact, there is two possible symmetry. Generally, I can call this we call anti-damping, or sometimes, by simplicity, we call spinor effect. It should be the most important for the spinor effect. But in fact, it can be due also to the hash bar effect. And this one, we call it field-like or hash bar. But in fact, the terminology spinor effect or hash bar is for simplicity. In fact, there are two symmetries that can be given by both mechanisms. And so, in fact, we have tried all these situations, and I do not consider I have the time to consider this situation where the current is perpendicular to the magnetic stripe. I will consider only the situation where the current is parallel. And the surprise was that only one situation, a single situation, is working well. Near walls, parallel currents, anti-damping torque, and then the only one leading from the symmetry of the situation to a steady motion, with the surprising result, first, that it occurs only for near walls. That is not the usual situation. It's very difficult to stabilize a near wall in normal condition, I would say. And also, the calculation was given opposite direction for opposite chirality of the near wall. And so there was surprising, and then the explication that finally we are proposing in a work with André Thierville is that to introduce that the dialogue-moyen interaction interface, what we have already seen this example of cobalt nickel. And so this is a paper where the calculations were performed, and so the physics is that the dialogue-moyen interaction stabilize the near configurations with a given chirality. And for example, the result is that the stabilization of the neural makes, for example, that the Walker breakdown that destabilize the domain walls is repelled at higher and higher field. And so finally, this due to we see that the Walker breakdown is suppressed, and when the motion is induced by spinor effect, by introducing larger and larger dialogue-moyen interactions, so they stabilize more and more the near wall and allows to take advantage of this good situation, domain walls plus spinor effect. The DMI domain, chiral domain wall plus. So this situation has been confirmed by several experimental results, including those by that will be presented by the next speaker. And so this is the first demonstration in this paper in last year. And if we make DMR is